here we go. Hi guys, welcome back. So today we're going to be talking about our homework 3 for transport 2. So here's the situation. So here's a tube. Let's see. Here's a tube, and there's air blowing across this tube, and at the bottom of the tube there's a liquid mixture of methanol and acetone. And then the mixture evaporates to the top of the tube, and that's where that stream of air is in excess. So at that liquid interface, Z is equal to 0, and then that total distance of that vapor phase is at where Z is equal to delta. And then here are all of our constants, all of our given conditions. So Y1 is the mole fraction of acetone, and that is 3.19. And then the mole fraction for methanol is 0.528. And you can just make Y3 to equal 1 minus Y1 minus Y2 because they should all add up to equal 1. And then delta is 0.24 meters. The temperature is 328.5 kelvins. The pressure is set at 99.4 times 10 to the 3 pascals. And the gas constant is 8.314 joules per meter times Kelvin. So then let's set some other variables. We're going to make 1, oh, that's the wrong thing. We're going to make 1 equal to the acetone. Two is for the methanol, and 3 is for the air. And then these are our Maxwell-Stefan diffusivity constants, and they are given here for 1, 2, 1, 3, and that's 2, 3. So then we want to calculate the molar fluxes of acetone and methanol. And the diffusion in the tube only takes place in one direction. So the evaporation moves in the positive z direction, and the air moves in the negative z direction. However, the molar flux for air doesn't dissolve into water, so we're just going to say the molar flux is 0. So given these Maxwell-Stefan pair diffusivities, we can solve for the molar fluxes by solving the Maxwell-Stefan equations. So I'm going to write out the equations for both the change in mole fraction of acetone with respect to that distance of the tube, Z, and then I'll also do the same thing for the methanol. So I'm going to write those out really quick. So this is the mole fraction for acetone with respect to the distance. Molar flux for the methanol. Mole fraction for the methanol. Molar flux for the acetone, all over that concentration and that diffusivity, Maxwell-Stefan diffusivity pair. And then just going to continue this equation. The mole fraction for acetone, molar flux for air minus, which we, this part of the equation, that's just that Y3, which we talked about earlier, over that concentration for the diffusivity pair, Maxwell-Stefan diffusivity pair for acetone and air. Then the same thing for the methanol. That's the methanol mole fraction, the change in methanol mole fraction with respect to that distance Z. oops, I forgot that mole fraction, that molar flux for acetone on that first part of the equation. Oh, that's a large 3. Okay. So now, later I can use these differential equations and the given initial conditions to be able to integrate and solve these as an IVP problem, initial value problem. But first we need some initial guesses for those molar fluxes, because those are not given. So what we want to make is an educated guess using an order of magnitude estimate. So I want to scale the driving force. I want to scale it so that the independent variable and the dependent variable are in a range from 0 to 1. So I know this dependent variable is already from 0 to 1. Those are mole fractions. But now I want to make the distance also range from 0 to 1. So I'm going to make this variable eta. And then from here, I want to take that distance z, and then I want to divide that by that total distance of delta. I think I might have said eta for this earlier, but that's delta. So that's that maximum distance, that's 0.24 meters. And by dividing these, I get a dimensionless number. So then we want to put that and apply that to these differential equations. So let's do that now. So I'll do the one for acetone. So here's that mole fraction, that change in mole fraction for acetone with respect to distance. But we're going to use that new eta. And then multiply it by that change in distance for eta with respect to that change with that distance z. So this just comes from an application of chain rule. And then as a result, we obtain 1 over delta. There's a change in distance, the change in mole fraction of acetone over that new distance that we scaled, eta. Let's see if I can make some more room. Okay, let's move over to the right some. So now we want to plug the, we want to apply this to these Maxwell-Stefan equations. So let's do that. But I'm going to move this 1 over delta to the other side, and I can just combine that with that concentration and that diffusivity constant. So hopefully I have enough room. So here it is. So all these other variables are going to stay the same over here. I'm going to need more room. And I'm just going to subtract this because that molar flux for 3, like we talked about earlier for the air, is going to be 0. So I'm just going to take that out of the equation to make things look a little bit better. And then I'm also going to replace this with y3 to simplify things with that molar fraction, that mole fraction for air. But we just need to pay close attention to that subtraction sign. Make sure we don't forget it. And the same thing for methanol. Same thing, I want to Hold on. This is supposed to be Y3. And that's also supposed to be 2,3, I believe. No, that's a 1,3. That's 1,3. This one's 2,3. Then don't forget that delta. Okay, so now I want to talk about the order of magnitude for these. So at the top, we know the order of magnitude is going to be 1 for the mole fractions. And at the bottom, we just scaled that, so it's from 0 to 1. So that's 1. So as a whole, this side of the equation, the order of magnitude is going to be 1. This whole thing, the order of magnitude is going to be 1. So that means that on this side, we need this to be an order of magnitude of 1. So we already know that the mole fractions are 1, and that delta is 1. So that's going to mean that the ratio for the molar fluxes need to are going to change, and they need to be able to be a certain number, so the other side, so that this side is equal to 1, the order of magnitude is equal to 1. Okay, so let's now try to get the left side of the equation, of the Maxwell-Stefan equation, with the order of magnitude 1 to equal the right side of the equation, and get that to be an order of magnitude of 1. What is going on? Okay. So concentration equals that pressure over RT. Then we multiply that by, what we're going to substitute in is that Stefan-Boltzmann gas estimation that we can assume because it's a gas. And then put that all over delta. So let's start plugging things in. So we already know that delta is going to be 1. And then we want the pressure to be, an order of magnitude of 1. And then the pressure is 10 to the 5th pascals, order of magnitude. R is 8.314, so we can just estimate that to be 10. And then that temperature is 328.5, so we can estimate that to be 100. This Stefan-Boltzmann gas estimation, we know that it's going to be 10 to the negative 5th. You simplify that out, that's 1 over 1,000 over that 1 for that delta. That does not look like a 1. And then we get 10 to the negative 3. So then that leaves us to know that our estimation for our, so the denominator over here is going to be 10 to the negative 3. So if we want an order of magnitude to be 1 on this right side of the equation, we want our initial guesses for the molar fluxes for acetone and for methanol to be 10 to the negative 3. Alright, hi, welcome back. Now we're going to be doing part 2 for the homework 3, and we're going to get into the coding. So first we want to start off, and we want to import a numerical library because we're going to be doing numerical calculations. So I'm going to start by using numpy and abbreviating it as NP. Then we want to use something called SciPy. So we're able to solve our differential equations. So another word for solving differential equations is just to integrate. And we want to import it as solving an IVP. Then we want to use SciPy again to be able to use the package called optimize So we're able to use use root findings. So let's type that in first, and then I'll explain it. So then we want import root. So we're able to find our root findings. So the situation here is that we're given initial conditions, but we also have two unknowns of the Molar fluxes for acetone and methanol. And we know that at the end, at the other side of this tube, is an interface where it meets the air. And here we know that the molar concentrations for methanol and acetone are going to be 0 because air is in excess. So we want to be able to adjust those molar fluxes at the other side until we get the molar concentrations to be 0 for the acetone and the methanol. So now we want to use Plotly because we want to be able to plot the mole fractions in relation to the distance, and this will allow us to plot them side by side. So then we want to import plotly.graphs.graph objects because we want to be able to graph these as scatter plots, and scatter plots are just objects, so that's where we put objects there. And to simplify it, we abbreviate it as graph objects. So that worked. That worked. Okay. So now we're going to move on to the variables. So this is the Maxwell-Stefan pair diffusivity, 1, 2, 1, 3, and 2, 3. And we're given these values in the problem statement, and these are in meters squared per second. Then we're also given the pressure and temperature for the system in pascals and kelvins. And then here is just the gas constant in joules per mole times Kelvin. And then from here we can get the concentration by assuming this is an ideal gas, and ideal gas system, ideal gases, with using PV equals nRT, so concentration will equal the pressure over the gas constant times the time, and it will be in moles per meters cubed. And then delta is just the tube length, which would be 0.24 meters. So these right here we get by looking at this Maxwell-Stefan driving force. And so what we did here is we scaled our independent and our dependent variable. This is the independent, dependent, so that they range from 0 to 1. And by doing this, we remove the units. And so when we take the derivative of this, our scale in relation to our scale position with respect to z, we get that eta, Okay, so then by taking the derivative of this driving force of our scale position with respect to z, we get from chain rule an eta over here, but it moves over here. So then we can simplify that by by making these f's variables. And then the concentration times the diffusivity over the delta for 1, 2, 1, 3, and 2, 3. Okay, so now we're going to look at the molar fluxes, our initial guesses for the methanol and the acetone. And it's going to be in moles per meter squared times seconds. So what we're looking at here is just the mole fraction over the dimensionless distance of eta, and this is just the gradient. So the order of magnitude would be 1, since the scales are from 0 to 1. So that also means that the ratio of the molar flux over this f variable would also have to be 1. Okay, so then these, and then lastly, these are the, oh no, oh no. Lastly, these are the molar concentrations at the interface. So that would be here. Okay, you're done. Alright, so now we're going to be starting the coding to solve the IVP. So let's do that. Solve IVP. And now we need to set the parameters. So dy is going to be our function. Then our t-span is just going to be from 0 to 1, because that's the range for our independent variable eta. Then y0, that's just our interfacial mole fractions. So that's just going to be, and that's given in the problem statement, and we already went through that above. For the acetone and methanol. Then method, Rado, oh, mess it up here. And then I just want to put dense output to equal true, so that we can evaluate the solution at any point, at any time. Okay, so now we need to define that function. So we're going to define dy, and then we're going to say eta and y, so the array of our mole fractions for acetone and methanol. Oh, almost forgot. I need a colon there. Down here, and you need to tab that. So then we're going to make our mole fraction for acetone equal to this, so that it's easier to input into our expressions, because in Python, the indexing starts at 0, not at 1, so inputting this whole thing into an equation might get a little confusing, so it's easier just to make it equal to y1. So we have that that constants, the consistency, that's the word, and hopefully reduce the amount of coding errors we make. Same thing for the methanol, except starting at 1. Oops. Oh goodness. And then the mole fraction for air is just going to be 1 minus y2 minus y1, because all the mole fractions need to add up to 1. Okay, so now we want to return a value, right? So return this to be tabbed over, then NP, and we want it as an array, since our mole fractions are an array. Okay, so now we have to write out our expression starting here. So the mole fraction for acetone multiplied by the molar flux for methanol minus the mole fraction for methanol multiplied by the molar flux of acetone, close that parentheses, put it all over F12. Then I want to subtract, because I'm taking out the middleman here, and the molar flux for air at that interface is going to be 0, because the air isn't getting into that tube, and it's only going across the top. So then multiplied by that mole fraction for acetone is obviously going to be 0. So we're just going to start off right here with that negative sign, and then all of this, as we defined earlier, equals y3. So we're going to start with the mole fraction of air multiplied by the molar flux of 1, and then put that all over F13, which we defined earlier. comma, then enter, then we're moving on to this expression. So same thing, I'm going to start with the mole fraction of the methanol multiplied by the molar flux of acetone minus the mole fraction for acetone multiplied by the molar flux of the methanol. Let's see if that looks right. Looks good to me. That all over F2312. Subtract that, do the same thing, take out the middleman, start with Y3, which is the mole fraction of air, multiplied by the molar flux of that methanol over F23. Okay. That looks good. Okay, let's try, and then, oh, okay, so then we also don't have the molar fluxes defined yet, so we should put that in. And we're just going to equal that to our initial guesses that we talked about earlier, that we got from the first part. Looks right. Okay, so now what we want to do is we want to do the root findings. So root is when what you are returning is 0. So we know our initial guesses were wrong. So let's just do is dot solve 1, because this is too big. These are supposed to be 0 for solving this IVP. These should be 0 for the mole fractions for acetone and methanol. So we know that our initial guesses for our molar fluxes for acetone and methanol are incorrect. So that's why we need to do the root findings to find the correct molar fluxes when the mole fractions of acetone and methanol at the other side of the tube are 0. Okay, so we can get rid of that. Shift over that. Okay, so the first thing we want to do is define this function. I guess I can leave that. So defining the function as f, and then this is just the array of molar fluxes, colon. And then I'm going to do the same thing as I did to the mole fractions earlier and create the arrays, because we aren't going to be using those initial guesses now. So the indexing starts from 0 in Python, so we just want to make it easier so we can plug it into our expressions later. So same thing as before. Okay. So then we want to evaluate the solution again. So we want to return a value again at the where eta is 1, because that's where we want those mole fractions for acetone and methanol to be 0. Indentation block. Oh, this all should be indented. Actually, yes. Okay, yeah, that was the problem, the indentations. So now let's evaluate the root. And then for the parameters, it wants the function, which we defined above. Then we want those initial values for that, those initial guesses for those molar fluxes. And then let's just evaluate there. And then we can see that here, it's stored in an array. The molar fluxes, these are going to be the correct ones after doing that root finding, and it's stored in a value of x. So then let's just store this in a variable so we can access it. And then change this so that we can use the correct molar fluxes, bringing back that x value, that correct molar flux for that. This is one is going to be for the acetone because this is the first in the array, and this is for the methanol. And then now we just want to define this function again because we want to plug the correct molar fluxes into the Stefan Maxwell equations. I think that's fine. Okay, so then I lost my train of thought. Let's see. Oh, we want to plug those molar fluxes back into the max and Stefan so that we can get the correct, so then we can plot those mole fractions over that that distance from 0 to 1. So that's eta. That's scaling for eta. So we can plot those as a scatter plot, all those mole fractions. Let's shift enter. Okay, cool. So now we want to get those plots for eta. So that would be our distance. So let's just, we want those to be our eta plots. Use numpy and then line space. So then we can get those increments for what we want to use for the plot. So I want it to go from 0 to 1, obviously, because that's what eta is, scaled by. And then let's just say we want 51 points. Or as it says here, the evenly spaced samples. So just our increments. And this is how we're just going to plot over eta the results. And so let's just do this first. So the 0 to 1 is just from the methanol and the acetone mole fractions from the interface all the way up to that screen at the top. Okay, that worked. Now we want to make those figures, so I want to make those subplots. Even though it's just going to be one graph. We're just going to put the methanol, acetone, and air onto that graph, that scatter plot. So we're going to make the rows go to 1 and the column. Oh, don't need to spell that all out. And then we want to add those lines, so we're going to start with acetone. So we're going to add that line. Trace is just another word for a plot, for plotly. Geo, that's the abbreviation or the variable that we gave for graph objects. And we want it to be a scatter. So that x is going to be the eta plot. So that's just going to, ooh. So that's just those the eta, so from 0 to 1, that distance. So we're going to plot that as the x value on the x-axis. And then for the y-axis, we are plotting the mole fractions. So with the index at 0, starting at 0, that means that we're graphing the acetone, which is what we want first for this one. And then the name, we're just going to put acetone. Okay. And then I'm just going to copy this because I want to do the same for methanol. So the only thing I need to really change is this. So that's for the methanol, and then change the name, obviously. Once again, copy paste that, except for this, I'm going to do the 1 minus the so we already have 0 there, so now we need the 1 for the other index. So the mole fractions of the acetone and then the methanol. So all the mole fractions should equal up to, for acetone, methanol, and air to be 1. So that's why we can do this. Oops. And then just change this to air. Okay, let's see. Okay, and there we go. We have our plot. And then the only thing else I'll add is just that if we wanted to plot for the x-axis, the distance to be for the actual distance, you could just multiply this eta underscore plot by the delta, because delta is that 0.24, that total distance, the actual distance in meters, and that's how we could just get the actual distance to be plotted. But besides that, I think we're good.